everyone for coming along today. I'm very pleased and excited to be able to share with you some exciting research that we've been doing in New South Wales. So just reiterating, I'm coming from the New South Wales Government Environment, Energy and Science Group, and also from the University of Sydney. I'll mention University of Wollongong as well, because we've been collaborating with Colin Woodruff's group, particularly looking at the sediment analysis that I'll be describing today. So that's the title of the talk, a few things in there to get through. Let's see how we go. I'll give a basic introduction of the setting, just some important aspects to point out, and our motivation for what we're doing in this research. So most of you are probably familiar with the New South Wales coast in southeastern Australia. It's about 1,000 kilometres end to end in a straight line, or about 2,000 kilometres if you follow the coastline, nooks and crannies. We can divide it into two halves, sort of a northern region and a southern region. And the entire coastline is wave dominated and microtidal, and characterised by a relatively narrow continental shelf. So you can see the distance there. It's only sort of 40, 50 kilometres wide, even narrower in some places. So the northern shelf, just looking at the bathymetry here, you can see it's quite shallow, the inner shelf. So the 100-metre contour is almost at the 200-metre contour, which is sort of considered our shelf break. So it's a narrow but shallow inner continental shelf, inner to outer continental shelf. And it's oriented sort of north-south. You can see some wave roses along here, giving an idea of the common wave directions. The southern shelf is a little bit different. It's similar in width, but it's a lot deeper. So we see the 100-metre contour bend in away from the 200-metre contour here. And the southern shelf is sort of characterised by a steeper inner shelf and a deep outer shelf plane. And the coastline is much more embayed. So lots of rocky reefs and headlands along the coast and deep embayments with coastal barrier systems. The wave climate varies a little bit along the coast, but is more or less driven by south to southeasterly waves. So the motivation for our coastal seabed mapping program, and essentially most of our coastal research program, of course, comes back to coastal hazards along the New South Wales coast. So I'll just briefly introduce those. Obviously, it's a wave-dominated open sort of shelf setting. So coastal erosion, beach erosion driven by large storms happens relatively frequently. This is some recent impacts at Womberall Beach that you might have seen in the news headlines. So this is sort of on the central New South Wales coast. And what I'm showing here is this is before and after a storm in 2016. And these are the impacts of a recent storm in 2020. So fairly regular sort of event-driven storm erosion on our beaches. And obviously the impacts to the beach environment and coastal development is evident there. Other parts of the coast, particularly the northern shelf, suffer the impacts from shoreline recession. So this is where we have an ongoing retreat of the shoreline due to a sediment budget deficit or a shoreline realignment. And obviously with rising sea levels, we expect to see this type of mean trend shoreline retreat more and more. So in terms of a global context, what is our coast look like and how does it respond to storms and sea level rise? I've just got the classic models here of sort of encroachment, the Bruin encroachment model, and the barrier rollover model as well. And I guess these are the responses that we get in the long term due to sea level rise and long-term processes. But at the event time scale, it's very similar. Our coast is very much a coast where the beach and dunes are quite well developed. And when we have storm impacts, the sand is moved offshore into surf zone bars and beyond the surf zone across the upper shore face. So this is actually the bathymetry at Womberall Beach after that storm in the previous video. We don't so much see these barrier overwash and breakthrough processes, simply because we don't have any of these low-lying barrier island settings. There are some low barriers on the northern New South Wales coast, and this is something that a process that we might see into the future with sea level rise, depending how the barrier systems respond. So to get our handle around what the problem is in New South Wales, we carried out an exposure assessment a few years ago, which was written up. And we came up with some pretty scary numbers about what might be exposed to beach erosion and shoreline recession. And the numbers are here in terms of now, sort of 2050, mid-century, and by the end of the century. And these plots are just breaking that down by region from north to south. And each stack is now 2050 and 2100. And the warmer shading is basically properties that are more heavily affected by erosion. So almost 100% of a property lot affected. So this second pass assessment, we called it, gave us a good appreciation of distribution of potential problems and impacts along the coastline. And also how exposure to coastal hazards is likely to grow into the future with climate change and sea level rise. There were a few problems with the assessment, however, which really came down to a lack of data and knowledge about our coastal systems. And this was most apparent in looking at the shore face. By this time, we had terrestrial LiDAR coverage, so high resolution topography along the entire coastline, and we were able to average the morphology along shore of our beaches into quite accurate profiles based on that high resolution data. But when it came to offshore, we didn't really know too much about what was going on out there. So what we did was basically came up with shore face profiles for all of our 700 plus beaches along the New South Wales coast. And we did that by just averaging in a compartment classification out to the 10, 20, 30 and 40 metre bathymetry contours. So you can see our conceptualization of the shore face was based on a few points at regular depths and fitting a profile through that. So of course that's very generalized, but it was what we could do at a regional scale at the time. So our understanding suffered from generalized shore face bathymetry, not a lot of data out here, an assumption that the Bruin encroachment model would occur everywhere, and an assumption that the shore face and inner-continental shelf was essentially all unconsolidated sand similar to the beach system. So that's sort of an overview of the setting and the problems. The outline for today's talk is here. 5 aspects that we'll step through. Firstly, just some background on shore face morphodynamics, so we're on the same page. I'll then introduce our seabed mapping program and show you some of the really exciting data that we've been collecting in the recent years, and how we're using that to address those problems I just talked about in terms of a lack of understanding of the shore face inner shelf environment. And then looking a little bit deeper into the sediments, what can we discern from what we see on the seafloor in terms of sediment movement between compartments and the processes that drive that. So I thought the shore face was sort of dead and buried recently. It had its heyday in the 90s when the shore face would appear on the cover of books about beach morphodynamics. And I saw this book recently, and shore face had dropped out of the beach system, dropped out of the title. 0 mentions in the table of contents of the shore face. 2 questionable mentions in the index, one relating to the shore face translation model and one relating to bathymetry. And it seemed that despite Ian Goodwin's 62 references to the shore face in his chapter, it was largely absent from this book. And this is just a little bit of fun, of course. And then came along Jack McCarroll in this talk series, and Jack bravely stepped forward and put the spotlight on the shore face again. And that was to the apprehension of much of the audience who were grasping their faces at the start of the talk, concerned that somebody would mention the shore face again. What happened from there was a flood of review articles about the shore face. Presumably, people had been sitting on this information for years, not ready to put it forward, but following Jack's talk, we've basically seen the second half of the year filled with a spotlight on the shore face, which to me is quite exciting. So I'm going to pick up on a few of these, recommend these papers. I'll pull some figures out of Edward and Troll's recent paper and thank them for doing a lot of good work in prettying up some of the older figures so I could use them here today. So the shore face itself, what is it and what does it do? If you're unfamiliar, you'd be familiar with the beach and the surf zone. And these are elements of the upper shore face. But the lower shore face is essentially this wave sculpted profile beyond that area. And the key difference between the lower shore face and the upper shore face, I guess, is the lower shore face is sort of sculpted by wave shoaling processes. If we're just thinking in the cross-shore domain in terms of sediment transport processes, whereas the upper shore face is shaped and modified by breaking wave processes. So we have our surf zone bars. You can see the difference in bathymetry, the difference in shape, and this sort of inflection between two profiles that we'll come back to later in the talk. But basically, this is a sedimentary environment, a depositional environment, both of which is connected to the beach, and changes out here can have important repercussions for changes on the beach itself. So I like to use this diagram a little bit. It's very simple. It's the classic diagram of coastal morphodynamic systems and comes from some of the earlier work there. The thing I want to point out here is that when people hear the term morphodynamic, they straight away think of changing form, so the topography or the bathymetry changing through time. But really the most important part of the morphodynamic system is the feedback loop that connects back to the processes that drive changing form. And the upshot there is that change in the morphology and the beach shore face system then influences the processes themselves, changes the sediment transport and goes through and changes the morphology. So what that all means is that the system can drive itself. It's not completely dependent on external forcing from the wave climate or sea level change, for example. Once the boundary conditions change, the system can continue to evolve even after the boundary conditions cease to change. So an important concept that we'll talk about today is the morphodynamic state of the shore face. And this came out of some work by a PhD colleague of mine, Mark Daly, and Peter Cowell, my supervisor, and Mark's supervisor. And they conceptualized three sort of morphodynamic states of a shore face if we were to try and determine what was going on in that morphodynamic system at a point in time. And the way to conceptualize that is to compare the surveyed or the known bathymetry of the profile with a theoretical equilibrium surface. So if things were in equilibrium, the waves would sort the sediment into a nice concave profile. If they're not, well, what does that mean? So they came up with three models. One was underfit. Essentially, the shore face profile is below the equilibrium surface, so there's not enough sediment out here. The next was disequilibrium overfit, where the shore face profile is shallower than equilibrium, so there's an abundance of sediment out here. And the third being a sort of classic conceptual model of the shore face being in graded equilibrium, so the sediment sorted across that domain by the wave processes. So that's a nice model, but what do we know about those concepts, and is there any evidence of them? Well, we have found some evidence of those processes, and we look to the geological record for one example of that evidence. So this is some work that we wrote up in 2016 from my PhD thesis. And what we found returning to this site at Foster Tuncurry on the mid-north coast of New South Wales, extensive barrier systems have built out over here over hundreds of thousands of years, and this Holocene barrier built out over 6,000 years. What we were able to demonstrate, developing some earlier work of Peter Cowell's, I was using a slightly different modelling process, And what we're able to do was reconstruct that through time, the process of a disequilibrium overfit shore face, lowering through time, and that sediment moving on shore to build out the barrier. What we found here was 80% of the sand came from the shore face offshore and 20% came into the system from around the corner. Important thing to point out here is that the rates of change are imperceptible if you're thinking of our human timescales and being able to measure things. So the total lowering was about 6 meters, so about 1 meter per 1,000 years of lowering offshore at a rate of 1 to 2 millimeters per year. So it would be very difficult to discern to go out and measure that in a few years or a couple of decades. Some more recent work from Tom Oliver, who's at UNSW Canberra, put together a similar story based on a lot of his great work in dating the chronology of barrier systems a little bit further down the coast. And Tom was able to put together a regional story which showed the interconnectivity of several barriers and that process of sand coming in from the shore face and building those barriers out through time. So the point to make is that the geological record shows us some evidence of these processes happening. The question that we want to know is, where are they happening today, and are they happening at meaningful rates of change? So an important figure here of just conceptualizing what's going on the shore face in terms of timescales. Everyone would be familiar with a classic closure depth based on Hallemeyer or Birkemeyer or Rob Nichols' work. And that closure depth is typically looking at our upper shore face only. So it's providing a limit on the sediment budget at what is essentially an annual or multi-year timescale. Beyond that, though, there's all this other sediment movement to understand out here on the lower shore face. And I just want to introduce the concept of the active zone, because I'll show you some animations of this shortly. But the lower shore face is the ultimate limit. So over geological time, our shore face profile might evolve into something like this, some sort of equilibrium concave form. The active shore face is a rate or timescale dependent concept, and the active zone is basically describing, if sea level's changing at a certain rate, which part of this profile is changing fast enough to maintain its shape. So this part of the profile below the active zone might be left behind, but this part of the profile might be able to migrate or translate with sea level change. And that really comes into those sort of translation type models of predicting shoreline response to sea level change. Importantly, the active zone isn't necessarily the same as the upper shore face. So it might be here over the timescale of 1 year, but if the rate of change in the timescale is longer, the active zone might be anywhere in here. And the upshot of all of that is, well, what is the offshore limit of the sediment budget if we're thinking about sea level rise over 100 years or so and at different rates of sea level change? So I'll provide you a little example to conceptualize the active zone here. And what we're going to look at is returning to Tuncurry. This is a hypothetical simulation, so just an exploratory model. We're starting here and we're going to look at 80 meters of sea level fall at four different rates. So a slow rate of sea level change of 1 millimeter per year, and then increasing to a more rapid rate of change of 10 millimeters per year. And this sort of encompasses the rates of change that we see in the geological record in terms of quaternary sea level oscillations, and what we're thinking about in terms of projected sea level rise into the future, hopefully not too far up here. So I'm going to play these videos, and what the videos are going to show is this process here, except we're going to normalize the shore face, so maintain the origin at the same point. So we'll just see the shore face profile evolve rather than the whole thing translate across the continental shelf, as is the case in the diagrams here. So what you'll see is, for the slow rate of change, the active zone is quite broad, and the process is able to maintain that profile as the system is translating across the shelf. What happened down here was the system translated so rapidly in response to the faster rate of sea level change that the wave processes that we'd calibrated for our Tungkari setting are unable to maintain the active zone except for the very upper part of the profile. So the summary of that is in this slide here. And if you're interested in these sorts of concepts, they're written up in a recent chapter from Peter and myself in Laura Moore and Brad Murray's Baryodynamics book. So that includes this plot here. But what we find is for slow rates of sea level change, the shore face profile is steeper and more concave. The active zone is wider because the active zone limit is deeper. And shore face translation across the substrate is slow. So there's more time for depth-dependent wave erosion to maintain a profile near equilibrium. So our classic Brunn type or shore face translation model has meaning to a deeper depth on the shore face. That changes for faster rates of change where the shore face profile becomes flatter and less concave. So that's our example here, going from our initial shore face in black to our final shore face in red. The active zone is narrower and shore face translation is fast, so there's less time for depth-dependent wave erosion to maintain a profile near equilibrium. So what is the meaning of all of that, or why do we care? We want to know how important is this Brunn effect for predicting future shoreline change. It's a concept that's often applied. It's often applied as a concept for the upper shore face only, but the upper shore face is sort of defined on annual timescales. So if we're interested in 100 years of sea level change, what does that mean? We need to think, how relevant is this concept for the broader shore face? So some questions here: does the theoretical shore face sink exist? What are its dimensions? Is the net direction of a cross-shore sediment transport offshore? And what does variation in the geometry of the shore face between sites, what will that mean for our sediment budgets at different sites and our modelling approaches? So a few problems. When we jump out of the cozy modelling pouch where things are comfortable and controllable into the real world, all of these other questions arise. And we've dealt with some of them on the previous slide in terms of the morphodynamics. But then we also need to think about geological controls. So does the geological controls on the shore face, rocky reefs and the substrate, do they overwhelm that balance between wave climate and sediment type and availability? And is that shore face inner shelf zone actually a production house of sediment? It might be producing biogenic sediment itself, so changing the sediment budget within that morphodynamic system. So some questions there. I won't go through all of them, but principally we want to assess the active zone. We want to know what that is for different timescales and rates of change. And we want to know what the morphodynamic state of a shore face at a given site is, so we can determine the applicability of that Brunn concept. And what will happen when sea level rise slows or ceases? So we talked about the morphodynamic system, and when changing boundary conditions stop, the system continues to evolve. So there's some important questions there. So I've pretty much just described what's on this slide. What do we need to know about shore face morphodynamics in order to understand changing coastal systems when we change key boundary conditions like sea level and potentially wave climates as well? So just returning to our sort of conceptual graphic, our upper shore face, our active zone, and our lower shore face or maximum shore face limit, how do they relate? So I'm going to step now into our coastal seabed mapping program. And this is really the data that we're collecting to understand and try and address some of those key questions. So this is a huge effort from my coastal and marine science team. And our team's led by Dave Hanslow. It's a huge effort to do this type of data collection, processing and analysis. This is our tiny team here we're missing a few now, but almost 10 people. And I've just included Raf Cavallo from now Deakin University, but previously Collins Group at Wollongong, who we've been collaborating in on the sediment analysis. So big thanks to everyone's efforts in the process. So our program is really mapping the coastal seabed of New South Wales in high resolution for the very first time in most places. We'd previously had some contracts to collect some bathymetric LiDAR about a decade ago in some small places, but we're now doing this wholesale for the entire coastline. So seamless topo-bathy LiDAR along the whole coastline. And with our vessel and our team, we're going out and we're doing multi-beam echo sounding and seabed sampling to try and learn a bit more about some of these key systems. So everybody knows about LiDAR. The only thing to point out here is that with the contract that went to Fugro, they were successful on that one. They flew the survey with two sensors concurrently. So one bathymetric LiDAR and one topographic LiDAR sensor operating through the surveys. And the key being that that gave us sort of a seamless DEM of the coastline. And the results were pretty incredible. We got good data up to 49 meters water depth. So that's pretty much most of the inner shelf in some places, with the poorer results being closer to 20 meters. So just a graphic depiction of the process flying along the coast in a plane with two different sensors, and they overlap in that that particularly difficult to map coastal interface between the land and the sea. There's actually overlapping sensor data there, so that's quite important to resolve that area in detail. So you'll be imagining the other applications for that data in terms of beach morphodynamics research. The key data products, obviously a digital elevation model, relative reflectivity, which is kind of like the backscatter of LiDAR, and I'll show a little bit of that, and also aerial photographs where the surveys were flown during the daytime. So we're going to zoom into the Illawarra region where I am now, and this is Wollongong, about an hour south of Sydney and this part of our New South Wales coastline. I'm just going to show you some examples of the data in two compartments. So these are our secondary sediment compartments. This is the Wollongong Compartment, and to the south is this one, the Illawarra South Compartment. So before our program, our understanding of the coastal seabed was relatively poor. It looks detailed here and is detailed here because there's a port right here. So obviously navigation, there's some islands and reefs. So it's been surveyed here in detail in terms of the bathymetry. But even as we go south into the next compartment, the data becomes more vague and generalized. And these contours are based on sort of a decreasing density of soundings for navigation bathymetry. Obviously not much known about the sediment and reef distributions. So just to get you to visualize the different types of data and their coverages, this is the coastal LiDAR. So you can see from our coastal zone out into the water, about 30-35 meters water depth in these compartments, and giving us some really good understanding of what's on the bottom. We mapped both of these compartments with our vessel as well, and you can see that we're now filling in the entire sediment compartment with the high resolution mapping data. And that's the bathymetry, or the level of bathymetry data that we gain through that process. In terms of the geomorphology of the seabed, LiDAR reflectivity is sort of a new research exciting area in terms of trying to understand this data. It's a bit different to backscatter data. It probably doesn't tell us as much. It's pretty good at telling us where sand is and where reef is, but it's not very good in telling us different types of sediments. So maybe coarse sand versus fine sand. It doesn't pick up that quite as well. On the other hand, the backscatter data is very informative for that. So we're now looking here at some coarser sand and finer inner shelf sand blanket out here. So putting all this data together, we're starting to get a pretty good understanding of our seafloor here. Of course, the signal intensity data is all relative, so we need to go out and sample the seabed as well. We do that with a sediment grab sampler and a video system on our grab, as well as a towed underwater video sled. So you can see areas that we've collected sediment samples in this plot. I'll play a little video now, which is just to highlight the importance of the video data with our grab. We're coming down to the seafloor here, and you can see it's quite complex. You can see some sorted bed forms, some sand in those sand ripples. And in the middle between the sand ripples, all this pebble, cobble, boulder, sediment. And you can see that's exactly where our grab has landed in this case. So if we were to only drop a grab and pull up sand from one of the ripples, or gravel and boulders from one of the swales, we'd get a pretty skewed understanding of what's on the seafloor. So it's still important with all that data to be able to see the seabed, to provide that essential context in terms of the sediment distributions and sediment availability. So just quickly now, what are we doing with that data? I've showed you the collection of the data and the data types. We're doing a range of classifications to turn the seabed data into more informative products for us and everybody else. One of these is morphological based, so bathymetric position index and rugosity analysis. And my colleague, Michelle Linklater, developed these methods and found that these processes are pretty good for basically automatically mapping our rocky reef distributions versus sediment. We then take the sediment samples from the grabs, and obviously our backscatter data, and to a degree our LiDAR reflectivity is telling us there's differences in the sediment. So forgetting about the rocky reef areas, but in the sediment areas on this part of the seafloor. And you can see these are photos of grabs from these different areas. You can see the difference in sediment, color, grain size, and mineralogy, even between two shore faces here, quite different sediment. And we've obviously got an inlet system going on here. So we're also taking that data and developing sediment distribution classification mapping. So trying to assign the backscatter with some different colors based on our sediment types, which is really important for understanding the systems in terms of the coupled beach shore face system and thinking about sediment budgeting going forwards. So I'll return here to how we're using some of the coastal seabed mapping data to address the questions that I posed earlier on in terms of shore face morphodynamics. So returning to our model of morphodynamic state of the shore face, and we're going to now look at a real site, so in one of those compartments, and we're going to compare the surveyed profile data from high resolution mapping with some equilibrium surfaces. An important finding that we had in this process, and this was just published earlier in the year, some of that mapping data for the Illawarra South compartment and the shore face analysis. What we found was the classic Dean model of an equilibrium shore face profile really only fits the surf zone in our setting. So if we apply Dean's model with an appropriate factor for medium sand, we get a nice fit of our surf zone profile, but it doesn't fit our broader shore face profile in any way. And this largely comes back to Dean's model being an empirical model. So it's based on observations in different settings, principally in the surf zone and upper shore face. What I did find in this investigation was that some work that Ortiz and Ashton wrote up, that should be 2016, not 2020, sorry, a few years ago, using some of Bowen and Bagnold's earlier work, provided an equilibrium profile, a theoretical profile that we're able to calibrate for our setting. And these theoretical models are based on wave shoaling on the shore face. So it makes sense. A shoaling wave model fits our broader shore face profile, and observations in the surf zone upper shore face are sort of fit for where wave breaking occurs. Another finding here was that the Ortiz and Ashton model, it fits when you apply it beyond the surf zone. So if I was to fit this profile through the origin or the shoreline, it then wouldn't fit our profile well. And I'll show you some examples of that now, of this process of assessing morphodynamic state. So we're in the Illawarra South compartment, and we're just looking at this stretch of beach called Perkins Windang Beach here, and 4 profiles along that beach, just to look at how much the shoreface morphology varies in just one connected sandy beach. And we can see going from top to bottom, the black is our surveyed profile from high resolution mapping, and the grey thick profiles are our equilibrium profiles, so our Dean model fitting the surf zone, and our Ortiz and Ashton model fitting the broader shore face. And what we're able to do then is classify the upper shore face and the lower shore face in terms of that disequilibrium or equilibrium model. And what we found was the upper shore face is generally close to equilibrium, so based on this model. But then when we look to the lower shore face, we can see that at this part of the beach, it's near equilibrium. As we get further south, there's a sand body offshore and it's overfit, sedimentary. As we get further south, it's overfit again. So the profile is above the theoretical profile, but it's affected by rocky reefs here. And as we come even further south, there's a large sediment lobe outside the inlet of the Lake Illawarra here. So some big sedimentary and geological influences on shoreface geomorphology in this setting that we're able to assess through that process. So that's the morphodynamic state. What about the extent of the shoreface? So the lower shoreface limit, the active zone, those types of questions we posed earlier. We actually found some pretty exciting sedimentary evidence that compared very well to the model predictions. And the model predictions are based on wave data for this setting. So there's a long-term wave buoy sitting off the coast here. So we're able to calculate the theoretical profiles quite accurately in terms of the wave data used and obviously the sediment data used that we sampled ourselves. So one of those sort of exciting finds here is there's actually a notch in the shore face here where it's eroding into the sediment body. And that depth where that's happening basically compared almost perfectly with our theoretical prediction of the lower shore face limit. So the long-term extent of the shore face, if we imagine the system has been relatively stable for thousands of years and evolving, the shore face has been lowering into this sand body. And of course, our barrier system on shore here provides a little bit of evidence of that regard, being a prograded stationary barrier system. Some other examples were the offshore limit of shore face sand. So in these areas where the lower shore face is more depleted of finer sand, that limit of shore face sand that's similar to what's on the beach was again quite comparable to the theoretical lower shore face limits. None of this really tells us about the active zone because it's a conceptual thing and it depends on the timescale or the rate of change of interest. So we can calculate that using Ortiz and Ashton's morphodynamic depth of closure, for example, for a particular timescale. But we don't expect to see evidence of it in the seabed because it essentially depends what timescale we're thinking of. So the outcome for modelling all this, which was presented in that paper, was basically if we add in all that new information about the shore face, the rocky reefs, the changing profile from north to south, so where was it overfit or underfit, and we can apply a Bruin response model considering all of those things. So essentially apportioning the calculated response only to where it is feasible based on the seabed mapping evidence. And what we found, I won't go into too much detail, but just some plots of predicted shoreline change for those 4 profiles. With our compartment approach, which takes all of these things into account, we found very different predictions of shoreline change, future shoreline change in response to a 1 metre sea level rise, based on obviously incorporating all of that understanding. So I'll just finish now quickly, a quick flick through some exciting sedimentary evidence that we're reviewing at the moment and working on some analyses for. And this addresses some of those other questions about connectivity between our beach and shore face system, and also alongshore between different compartments. So just quickly, some features that we've been identifying. I mentioned we were also looking at a sedimentary classification. So we're using a morphological classification technique to basically automatically identify features in the LiDAR and multi-beam data. And what we're seeing here is some sand ripples that have evolved into shore transverse scour channels, which are showing in this open shore face setting. So this is in a setting that's quite dominated by longshore processes. It's showing some depositional evidence of a longshore transport outside the surf zone. So this is on our shore face to inner shelf. And also how that's affecting cross-shore processes. So these scour channels are sort of providing some evidence of sediment movement, of certainly hydrodynamics and potentially sediment movement from the surf zone out across the shore face. These profiles here are just along these lines, with the circle being the start of the relevant profile. Some other features deeper on the shore face, showing us some other evidence of a long shelf sediment transport and self-organization of different sediment types. These are features that have been observed in other places around the world and haven't really been noted in our setting because of the lack of data. So we've identified some sorted bed forms and some larger features that appear similar to shore-face detached sand ridges that have been described elsewhere. You can see the morphology here is sort of up to about 4 meters relief. The LiDAR is useful for identifying features, but the vessel-based research is really fundamental for finding out exactly what they are and what that means. So this is just showing some backscatter data that we've collected over some sorted bed form features and showing the difference in the sediment types or the organization of finer and coarser sediment and what's going on here. And what we're finding is the evidence is showing that the fine sand on the lower shore face to inner shelf, in a lot of cases, is quite thin in its distribution. Another interesting feature, just before I finish, now looking at sort of cross-shore sediment transport processes in the embayed settings, is these shore face deflation depressions. So we're finding these off prograded barriers, and what we're seeing is sort of evidence of the process I was describing earlier, lowering of the shore face. So our lower shore face to inner shelf is becoming depleted of finer sand, which is being moved onshore into our barrier system. So finer sand in these areas and coarser sand in these areas. So all of this is giving us an idea now of some numbers on the sediment budget, how much sediment is on the shore face, in the shore face system, and are these processes present and still occurring. And just finally, the last one, identifying headland bypassing pathways. So this is a Crowdy Head on our coast, and you can see this is actually a sediment compartment boundary, but there's quite a good pathway for periodic sediment headland bypassing in this region. So by identifying and understanding some of these pathways and processes, we hope to be able to get to a quantitative sediment budget at some stage. So our next steps in our program, the classifications, continuing the vessel-based mapping to really ground truth and extend what we're seeing in the LiDAR data. Seabed geomorphology, obviously we've shown some examples there, and mapping the pathways within and between sediment compartments. So the final slide just here, really the ultimate summary of all of this work is we want to come up with compartment sediment budgets, or what might be called total sediment budgets elsewhere. So not just along shore, but across shore within our within and between our sediment compartments. So we're really going from very little understanding to what I call the crown phase, which is where we're at now. We're able to put some ideas in terms of ins and outs on different processes where sediment might be coming from and being lost to within a given environment. And ultimately, we want to get to a numbers stage. So the next step from here is taking all of this insight and information and putting that into some models to come out with some quantitative compartment sediment budgets. So I'll finish there, and a little bit of time for discussion, hopefully.
Thank you, Mike. It was a really cool presentation. I've got severe data jealousy right now. We've got time for a couple of quick questions so that we finish by 4, if anyone wants to jump in. Questions? I could ask one. So obviously it looks like it takes a huge amount of resources and effort to get that sort of information. And not everywhere is able to do that. Do you have any thoughts on what you're finding out here? Could that be useful in other places where we can't go out and collect this information, or how could it be translated?
Yeah, I think in terms of coming up with archetype settings and identifying the processes that are happening in different environments, I guess the vessel-based mapping and sampling is very resource intensive in terms of time and money and effort. The LiDAR is really incredible. One of our key findings is, I mean, most of the shore face along our coast was